My name's Rob. I'm not a Nepali guy. I also forgot to get my hair cut for the presentation. I'll try to put that on the list for next time. But I am a JD, which is Latin for overpriced education that landed me nowhere. Actually, no. It means I'm trained as a lawyer. I used to be a police in the police forces in the U.S., and my specialty was technological crime and financial crime. Now, I'm only telling you that because what I'm about to show you does not seem like it has anything to do with that whatsoever. But I will actually relate it, but I want to show you how that relates through an actual project that we're doing at Softwarica College. So at Softwarica College, because I'm the only American instructor, I feel it's my job to abuse the students as much as possible. So we're doing a research project where we're using computer vision and a form of AI to analyze text. Analyze texts. I told you it was going to be super boring, right? So, computer vision. What's interesting about text is that normally we kind of all think like that's just obvious for computers, right? So like, you know, when you get a document, you search by letter or words or whatever, and you can find what you want to find. Same with numbers. Where it gets a little confusing, at least for the computer, and definitely for us, is what does the computer actually really see? So how many of you know what like OCR is? Give it to me in English. A lot of people don't know what you're talking about. It's basically like taking something that's not necessarily text and turning it into a text-based or a text-readable format, right? So essentially, we have an image of something. So it might be a PDF. It might be a PDF of a scanned document. To the computer, that's a picture, right? It's looking at it just like a JPEG of any kind. It could be your cat, could be whatever. To the computer, it makes no difference. So OCR is a way to train that computer program to see that picture more closely to how we see it and be able to search it and use it. But basically how it does that is kind of the same way it looks at everything. Computers are sort of dumb, even though we're calling them intelligence artificially, right? So, does anybody kind of know what that picture is? Has anybody seen something like that?
On the check.
Yeah, right? On a check or some other bank thing, right? So, this is magnetic ink character recognition. This was invented in the 50s. What this is how the computers read things like your check, or maybe like some kind of financial statement, credit card statement, or in the old days at least, even the credit card itself, right? Remember when you used to have to swipe cards because they had just that magnetic strip on the back, and now they have the fancy chip and all those other fun things. Now you can tap them and flip them in the air and your bill still gets paid. Well, in the old days, it was a magnetic strip, and basically it had something like that embedded into the strip, and that's what the computer read. Computer vision now is not all that different. It's just a bit more sophisticated in what it can interpret and what it can put out, okay? So, now we're looking at something a little bit different. And here's where it gets tricky, right? What the heck is that stuff on the right side? Anybody guess? What was that?
Numbers.
Numbers. Anybody else have a guess? I'm not saying he's right or wrong, whoever said that. Say that who? Some kind of handwriting, is that what you said? Some kind of handwriting? Any other guesses?
Alien language.
Well, the answer actually is nobody knows. So this is actually text from one of the few historical documents that nobody has been able to identify if it's even a language at all. Right? Now, lots of people have tried, still have tried. By the way, that text that this comes from is believed to have been written sometime between 1400 and 1450 or so in the Gregorian calendar. So 500-600 years old. And still nobody knows what it says. Now, the original script is actually in a very old book. So do you think it looks like this? No, not really, right? So up until now, what scholars were trying to do is they were creating a version of this to be readable by a computer. So how do you suppose they went about that?
They scanned the image, then pretty much they did a reduction.
You're on the right track. They were actually even a bit simpler and less clever than that. So they just took each one of these things, whatever they are, and they assigned them a Latin letter, because Latin letters is something computers can understand, right? And so then from there, what they did was they did an analysis based on a Latin letter representation of each of these things. And from the Latin letter, they created a picture that looks nice and neat like this, right? The problem is, it's not that nice and neat in the script. So there becomes this issue of what happens when we have things like here that are really close together. So what we're doing, because it hasn't for some reason been done yet, is we're actually taking the images of the characters not as they've been nicely portrayed, but directly from the text. And we're looking at the individual characters. So you can see down here at the bottom, there's in the color in here, it's a little hard to tell, but there's highlights of similar strokes in each character. So what we're doing is we're taking our computer vision program and we're running it against an algorithm called the SIFT algorithm. So the SIFT algorithm, basically what it does is it takes an image that the computer has looked at, and it's going to identify every point in that image. And in our case, our image is not just the page, it's also each individual character that we can extract. And so from each of those individual characters, it's measuring and plotting every place where the pixels are for each character. Now, what's cool about SIFT is SIFT doesn't care how big or small your input image is. So our input image can be any size, and it's going to scale basically it's going to take into account the scale of the difference of the pixels to tell you whether you have a matching pattern, regardless of whether the pattern is this big or this big. And then from there, it's going to run that comparison back against itself and be able to tell you how many of these characters match and by what percent. Right? So like I said, you've got a couple here that look pretty close. Are those two the same? Maybe. It looks like it there, but that doesn't mean that's what it really looks like in the script. So maybe our program can tell us those are 85% similar. And then when it compares all of them across the thing, it can tell us it's like 86.2% when we compare them all. And then we decide whether that's a match or not, right? So this is one way that we analyze text. Now, why do we do this? Because this sounds super boring, right? Who cares what this 600-year-old thing says? If nobody could read it till now, you know, what if it was the news, right? But where it gets interesting, though, is where this can actually apply in other places. So I mentioned at the beginning that I used to be law enforcement. We use this same process for a very different purpose. So we have all, you know, social media out there, right? Everybody here is probably on it somewhere. And if you're not, you're probably on somebody else's. I just got my selfie taken with 4 or 5 people, so I'm at least on 4 different ones, even if I didn't have one, right? It's kind of how it goes now. When we're looking for people, we were looking for, so I had a case where I had a person who was on the run. He was facing a very long sentence for some violent crimes. We actually located a picture of the person on some social media, and all we had was the background of the picture. Now, if you're familiar with pictures in social media, a lot of times there is no metadata associated with the photo, so we can't identify it from the underlying data. But we could use this process where we're mapping, and what we did in that case is we mapped the skyline behind the person. We didn't know, there was no other people in the picture. There was no identifying thing like, you know, it would be really nice to have like, you know, Rob's Deli, 823 C Street in New York City. We didn't have that, right? So all we had was some kind of random skyline. So we did the same thing. We identified particular features of it. And then what we did was we collected from the internet millions of photos. No parameters other than it had to be big enough to have a skyline. And we ran the same measurement against it. We just connected the dots with a variable scale, and we identified the skyline to within about a 75% accuracy. Now, when you have nothing else to go on, 75 is pretty good. We caught the guy 2 weeks later in the same parking lot the photo was taken. So this technique actually has a lot of value. Now here I'm showing a different script. Oh, by the way, before I was police, I was going to be a translator, like of ancient texts. And then for some reason, carrying a gun and running around in the backyard seemed more appealing for a while. I was a fireman before that, so clearly I can't make up my mind. So by the time this presentation's over, I might be on a whole different topic. Okay? But this is ancient, not all of it, but this is different variations of Tibetan script. So my first translation project when I was in college, which actually brought me to Nepal originally, was because I was translating one of those scripts, one closer to the bottom. It wasn't actually this one, but the one I did was closest to that one. So this is back when you guys were all younger, and I was still old. But as you can see, it looks quite similar, right? Had I had this sort of development back then, it might have been a lot easier to pick out these really close characters. Back then, what we had to do is we had to go search through old texts and try to find them in places where the translation was known. So there's a really strong practical use. The criminal case that I gave you was one example. Translating text is another. In this case, it's already being done, not by me, where they're taking some of the texts that are written in the script that have not been translated into a bunch of other languages yet, and they're creating basically a translation that will then be reviewed by people who actually know the language well to make sure it's correct. But that doesn't stop them from having to do some work, but it saves them a heck of a lot of time because, like I said, this looks nice here, but when you're looking in a 500 or 600-year-old text, they don't quite come out that clean. So if you can have this type of program in this process help speed up the effect a little bit and see if it can get you more accurate or at least a better starting point, saves you a lot of time. And then I wrote some really smart stuff down here because I wanted to make it seem like I really know what I'm doing. But I didn't actually want to get into the details. But it really is based on a mathematical principle. So we can use algorithms, the big scary word, right? Everybody hears about the algorithm. A lot of people have no idea what that means. Some of the people that write them have no idea what that means. So it's basically just trying to find a mathematical equation that accommodates your input in such a way that it can give you the desired output. So here's where the thing for me that comes in when it comes to AI, right? This is all very specific to what my project is, but it also is a very important piece of information. So as soon as you read this paragraph here on the right, I will tell you what that information is. No? Nobody in here reads Old English? Me neither, I don't know what it says. All right, so, but this is an example of what original text would look like, right? Much different story than all that neat stuff that I had up there before. But the point that I wanted to make about this project and about applying AI in generally, and all the much better than I speakers that came before kind of made the same point in different ways, is that there's nothing inherently wrong with AI itself. But it's very much in the application, right? if you're doing a specific project, you have to pay very close attention to what information you're feeding it in to know whether or not that's going to give you appropriate out, right? Our input decisions have to be very carefully made based on our output desires. Now, I don't mean you want it to come to a specific answer, but that you're looking for it to produce something based on what it's being charted to do. So you have to kind of think a bit carefully. Now, backpropagation is essentially the human part of evaluating the performance of the AI. In some of the bigger programs, that was part of sort of the process at one point or another. But the problem goes back to whichever of these guys mentioned the black box issue, right? Backpropagation is not as effective when you don't know all of what's in the data set. So for us, this is great because we could just take it, we can take our set and we can go look. So it's telling us, like, for example, these two characters are the same. This one has, to use the linguistic term, a squiggle on top. So clearly those are at least not the entirely same two things, right? And that's where we can go back to our program and say, this is the wrong parameter, this is not correct, and allow it to recorrect itself and try again. So we can get a much more accurate response or outcome. This is what they call, this is a reinforcement loop. Now, neural network AI is trying to make this step a bit more efficient. And it probably will at some point. But it's going to take time. And this is why they say, for example, you shouldn't just go and ask ChatGPT or one of these other ones. That's Microsoft calling, saying, hey, hurry up, get him off the stage because he's talking about ChatGPT. But when you're using an AI that uses a large or unknown data set, you should be cautious because you don't know how effective the reinforcement loop is, right? There's nothing wrong with using ChatGPT or any of those things. But if you're doing it to target a very specific sort of function, you want to make sure that what your input is and what the data set it's going to use to try to decide that outcome, make sure those goals align, or else you may not get what you want or what you expect. So, here's an example of one that was just solved recently, partly through this process. There was some other help. But this is linear B. It's one of the oldest found, discovered, written texts in human history. And they recently resolved this, or at least translated a reasonable extent of it. And they did it through this process that we're talking about in part. Obviously, there was some linguists and historians that were also helping along. But this is what I was just talking about. So, what we do with all this, and I'm just going to do this part really quickly because, this is like the boring stuff. But this stuff actually can be applied to a bunch of different processes, right? So, we have frequency analysis. Frequency analysis is a really bland way of saying sort of how many times stuff appears places. But frequency analysis is changing because in linguistics, it's great because we just count how many times a particular letter or number appears in a certain place in the text, right? So it helps us a lot with translating because most languages follow a particular frequency. I'll give you an easy example. Even if you're not native English speakers, how many in here know what the most likely letter to come after Q is?
E.
Second most. U, right? Queen, whatever other QR words there are. I'm still learning the language myself. But those things happen with a measurable frequency, right? So this is really useful for deciphering languages. It's also really good for deciphering code. Now, it used to be that frequency analysis only worked on basic ciphers, right? Like a Caesar cipher, or like ROT 13 or something, where you basically have just a shift. And that was all it could do. But now with the power of AI, You can do frequency analysis and account for shifts in text, which gives you a much better chance at being able to break a cipher, even if it's using layered encryption. You know, you've all probably heard everybody screaming, quantum computing's coming, all encryption is dead. We all should just go outside and forget about it. Right? We've been hearing that a lot. I'm gonna tell you a little secret. Where's the camera? Quantum computing can do certain things very well. Breaking encryption isn't one of them, and it's not gonna be. I actually have my doubts that quantum computing will be used in any mass scale encryption, decryption, anytime ever. Now there's a whole bunch of technical reasons for that. But it's not quantum computing we have to worry about. 256 AES. Anybody know what that is?
That's the most used encryption standard today.
I'm glad he's here because everybody else probably thinks I'm just making stuff up. Like I'm just talking and then all of a sudden I'm like, 256 AES, and they're all like, that's correct, right? It's the most commonly used type of encryption in most of our functions that we use, right? Wi-Fi, it's used in a lot of different encryption for websites, all these things. Frequency analysis has already been used to break it. Now, why don't we hear that? Well, because the problem is they were able to break one single one with sort of some pre-known information, right? So it was like a really sort of contrived laboratory experiment. But the point is they did it, which means when you start adding clever and flexible computation power to frequency analysis, you're going to be having to raise encryption up another step because that's not going to be enough encryption. That's going to be a much greater threat than something like quantum computing. Not to mention, quantum computing requires you to have a cryogenic chamber, which I have 2 in my basement, but I don't know how many of you have those out there, right? But this, so this is one example of how AI actually, carefully constructed for your purpose, coupled with techniques that we already use, can be really, really powerful stuff. And it can also be used in the reverse as far as like securing a system, right? So then we have another one, language entropy. There he goes again, just throwing out random words put together. He said language and entropy, whatever that is. But language entropy actually really is a thing. Basically, entropy is something you've probably all heard of, although more common in thermodynamics. All right, I have some nerds up here because I didn't even think that joke was going to land. I'm just kidding, I'm sorry. But that's correct, right? Entropy is basically just in linguistics, it's just the sort of predictability or level of information in a system. And what that means is just that you can measure a system, a linguistic system, and based on its entropy values, you can learn all kinds of things about the language. Now, this is actually pretty useful though, because you can do the same thing with encryption. You can do a certain level of entropy analysis with encryption to at least do a couple of things. One, it can help you identify the encryption. That's a really useful tool if you have sort of partial value or some other thing that prevents you from sort of getting the whole universe of information. But it also can be compared to other things that you can test on. So you can use entropy to test other value systems, because entropy itself is really just a measurement of a system, essentially a closed system, but even that has some flexibility. So you can use it to measure any part of a system, and then you can use it as a baseline to make a comparison when you have an unknown. Now, nobody's doing this on scale yet because it's complicated, and because when we're trying to use it at scale, the computational power is going to be considerable, and it's probably just not really been tested in the wild, but something like this will come as you get increased computing power. And of course, for many of you that probably know, I know he knows, you can get massive computing power by renting, essentially, because you can rent like GPUs online from, I think even Amazon does it, don't they? So you can rent at like, you know, orders of magnitude higher than you could ever do with even a room block of machines. So these kinds of analyses can be done. It's just that we haven't combined them all that much yet with AI processes, but once they are, you're going to see some dramatic changes. And then there's the Sukhotan algorithm. Now this one is specific to language. I was trying to think of a cool way to use this somewhere else, but I spent more time just trying to actually pronounce the algorithm name. But what this basically does is it uses its own sort of calculation to run against the language to where you can discern between vowels and consonants. So it's pretty cool for like decoding an unknown language. What's really cool about it is the bigger the set of text you run it against, the more accurate it becomes. So and I'm going to show you one quick example before I subject myself to your barrage of questions. But one cool example I'm going to show you in a second where they actually had a scroll that they weren't even sure exactly what was written in it, and they used this and some other methods. But this method, like I said, the more info you have, the more accurate this is, to the point where once you know for sure what is a consonant and what's a vowel, the ability to identify the language goes up to like 90%. So, and then there's Zipf's law. Now this applies to a whole bunch of things. Anybody ever hear of this law? It's basically like the law of the lazy. About right? Basically, Zipf's law, the principle is that in most systems, over time, and not necessarily by design, the system resolves down to like the simplest method of accomplishing the thing, right? So in a language, for example, words become shorter, words become less frequently used when they can be basically removed or changed, right? So the example here is, you know, math for mathematics. Now that's a very American English thing because the Europeans say maths. And when I say that in America, people look at me funny. So I used the American one just in case. But plane for airplane, et cetera. So Zipf's law is just a way of testing, again, another system, but it's typically used in linguistics, but it doesn't have to be limited to linguistics, where you can actually analyze the overall structure of the system from a complex to simplistic sort of trajectory. All right, so there's all my information. I made the links really small and really bad color so that it seemed like I was being open, but really I don't want you to follow me. Actually, no, it looked really good on my laptop. It still does, just up there it doesn't, so. And then down below I have a website where I write all kinds of fun stuff. About only, I'd say 15% of it is I like to pick on American politics, but the rest of it is kind of sciencey, math, and actually some of this stuff too. I wrote a whole article on what fuzzy hashing is. It wasn't popular. But anyway, so you're welcome to actually reach out, follow me, like, subscribe, share, whatever the term of art is, you can do that if you want. I believe that being someone that's sort of in a unique position of how I do this stuff, I encourage you to reach out to me if you want to ask me about like careers, if you want to ask me about technology, if you want to ask me about kind of anything, just, you know, no breakfast images. I don't really care like what your kids look like, it's no offense, it's just that I'm not going to know who they are anyway. And please don't send me weird stuff, you know, beyond those first two categories. I only have to say that because the first time I did this, it was a mistake. So now I put the disclaimer in there. But in all seriousness, if you do ever want to ask me something, I usually try to answer fairly quickly. It is kind of helpful if you tell me how I should sort of know who you are. Like obviously I'm not going to know everybody out here, but if you're like, hey, I was at that AI bootcamp thing, that would be better than like, hey, I'm at the balcony across from your apartment looking in your window. even if it's a cyber question, the lead-in might matter, okay? So anyways, I will open the floor to questions. Sure.
So, do you know of any other ways that these algorithms are implemented except from like linguistics and finding people?
The specific ones I talked about?
I mean in general, not those specific.
I mean, yeah, there's a lot of stuff being done from the cybersecurity realm trying to figure out how we can apply some of the principles to cybersecurity, because a couple of the issues with cybersecurity is automation is great, but automation doesn't necessarily keep up with the times. So like, is there a way, and there are some things happening, but is there some more robust ways to both automate but also sort of make flexible, cybersecurity systems? I did want to show you, but yes, so the other cool thing is, I wanted to show you just real quick. So this is what I was talking about before. Now, this is a cool example because this actually has medical applications, so kind of to your point. So Mount Vesuvius, big volcano thing in Vesuvius area. I was a historian of China, man. I don't know where this place is. I know it's like somewhere by Greece. Italy. All right, there you go. I told you, I used to carry a gun. We didn't have to study this stuff. But, big volcano, everything was sort of packed in the dirt and whatever over many, many centuries. And they recovered some of these scrolls. And I don't know if this, I want to just show you, that's what it looked like. I hear some giggling. Some of you have dogs. You're probably like, yeah. But that's what the scroll looked like, and they couldn't open it because obviously it would fall apart, right? But why this project is really cool is what they actually did was they did CT scans on this thing multiple times. This, like, I can't even call it burned out scroll. It's like a fossil. But they did CT scans on it multiple times to get as much of a picture as they could. And then this team, which by the way was led by some undergraduate students, which is even cooler, developed an algorithm to start matching up the patterns in the CT scan to see if they could decipher language. And they actually came up, I think it was like the first, like 85% of the first half of the scroll. And translated, they just did the AI output translation, and then they gave it to a scholar of this era of history who said, this is like totally reasonable that that's what it says. Obviously they can't know for sure because they can't open it, but that's pretty impressive, right? And so to your question, somewhere in the middle there, you, right? Sorry, I'm pointing at you, it's rude. To that question though, they're doing those same kinds of processes in terms of like looking at medical diagnoses. So like we were talking before about that. How can they come up with more predictive technology where we can identify really small anomalies before they become really big problems? So, and there's probably 5,000 other things that we could talk about, but those are some of the big ones. Anybody else?
As AI has been evolving day by day, how AI models can be used for dominating those bad AI softwares, like it can be harmful for AIs for some security, security purpose?
Security for, did you say a particular sector or just in general?
Particular sector.
Did you name the sector?
Yes.
Which one was it?
For like here, as our administration was told before that data in medical field are not be exploited. So how AI can use implement those exploiting of that?
Yeah. So I mean. There's not going to be a simple answer to that because it's going to be also responsive to what the new attack methods are and the new decryption methods. But one thing that is a really useful method just in general from a cybersecurity perspective is to not transmit, store, or otherwise like have all your data in one place, right? Now, of course, the problem with that is then you trade some efficiency if you're breaking up, sensitive content. But AI may be able to create, somebody may be able to come up with some clever way to break up information and transmit it across multiple different places and ways so that it can't be easily intercepted or all deciphered in one place in any meaningful way. We do that now to an extent, but I mean, to use sort of your example, trying to scale that up into some much broader thing is one way. I don't know that much about healthcare other than the cybersecurity issues are basically the same as anywhere else. Obviously health data is sensitive and needs protection, but so does financial data, so does, military secrets and all that. So the methodologies, I think, would be the same, but my guess is that the idea is going to be to reach a point where you're not relying solely on encryption. Encryption's a part of it, but what other ways can we employ AI-driven programs to, further layer our security, like ecostructure, outside of just one sort of path, like I said, like encryption as one example, right?
I wanted to ask you regarding the Tibetan translation project that you initially did. Like, how many volume in terms of size of data you needed to start with and things like that?
Yeah, so the question was essentially like how much of a data set did we use to run? So for the Tibetan project, that was my example to doing it without the AI. So we didn't do, that was like very non-technical. So we didn't do that at all. For the other text that I showed you, this one, so for this text, there's already been one attempt at it in a different methodology with AI. And they used what amounted to probably about, so this text, the original text that they're looking at, the undeciphered, is like 38,000 words. And I use that term loosely because we don't actually know if those represent words or not, but assuming those are words, it's about 38,000. So they ran it against 3 different corpus of text, which altogether I think was around the equivalent of 1 million pages per corpus, so about 3 million. Now that's a very loose number because again, it's kind of an estimate, but I would say about 3 million, and it was about 27 languages that it covered as far as that 3 million pages. So, and so far, but again, I think that their first go of it was kind of flawed because they were trying to use like this kind of clean made up version against it. But ultimately, they did not have any success. So either 3 million was too small of a number or the methodology was flawed. So, and that's why this process for us here is to try to make it a more accurate rendition of what the characters actually look like, not making any presumptions about what the meaning is, and let them just run it as a character-to-character match. So, but in the long term, it'd be a big project because you might have to go beyond 3 million for sure. So
like my question was that since language is generally inherited, one language inherits from some other languages in the past, and that kind of is there. Do you advocate that if we use more of old languages as corpus, then this process would be easier?
So yeah, I mean, I think that's right. So in this case, the idea was to start with contemporary, right? So stuff that was known to exist around 100 years, give or take, before or after the document's age, right? And of course, that's all based on carbon dating and that, so there could be some leeway in whether or not it was written then. But yeah, you could scale backwards and try to use other things sort of with the idea of a root language in mind. And I'm sure people would do that. The challenge there, though, is getting those texts and getting them in a format that can be compared then as well, because as you go back, the quality sort of goes down a little bit. So, but you're right, like from a conceptual standpoint, that yes, that would be ideal. It's just not always possible. So, all right, thanks everyone. I'm here every Thursday. Not really, no.